Grandmaster level in Starcraft II using multi-agent reinforcement learning. Many real-world applications require artificial agents to compete and coordinate with other agents in complex environments. As a stepping stone to this goal, the domain of Starcraft has emerged as an important challenge for artificial intelligence research. Owing to its iconic and enduring status among the most difficult professional esports and its relevance to the real world in terms of its raw complexity and multi-agent challenges. Over the course of a decade and numerous competitions, the strongest agents have simplified important aspects of the game, utilized superhuman capabilities, or employed handcrafted subsystems. Despite these advantages, no previous agent has come close to matching the overall skill of the top StarCraft players. We choose to address the challenge of StarCraft using general-purpose learning methods that are in principle applicable to other complex domains. A multi-agent reinforcement learning algorithm that uses data from both the human and agent games within a diverse league of continually adapting strategies and counter-strategies, each represented by deep neural networks. We evaluated our agent, Alpha Star, in the full game of Starcraft II through a series of online games against human players. Alpha Star was rated at Grandmaster level for all three Starcraft races, and above 99.8 of officially ranked human players. Starcraft is a real-time strategy game in which players balance high-level economic decisions with individual control of hundreds of units. This domain raises important game theoretic challenges. It features a vast space of cyclic, non-transitive strategies and counter-strategies. Discovering novel strategies is intractable with naive cell play exploration methods, and those strategies may not be effective when deployed in real-world play with humans. Furthermore, StarCraft has combinatorial action space, a planning horizon that extends over thousands of real-time decisions and imperfect information. Each game consists of tens of thousands of time steps and thousands of actions, selected in real time throughout approximately 10 minutes of gameplay. At each step T, our agent Alpha Star receives an observation OT that includes a list of all observable units and their attributes. This information is imperfect. The game includes only opponent units seen by the player's own units and excludes some opponent's unit attributes outside the camera view. Each action AT is highly structured, and it selects what action type out of several hundred, for example, move or build worker, who to issue that action to for any subset of the agent's units, which to target among locations on the map or units within the camera view, and when to observe the next act. Figure 1A. Figure 1A. Okay, let's see. Figure 1. Training Step A. Alpha Star observes the game through an overview map and list of units. Okay. To act, the agent outputs what action type to issue, for example, to build, which is applied to when it targets, where it targets, and when the next action will be issued. Actions are sent to the game through a monitoring layer that limits action rate. Alpha Star contends with delays from a network latency and processing time. So the action is move, attack, build, what, who, where, what action next. Real-time processing delay 80 milliseconds. Action limit 22 per 5 second. Requested delay 200 millisecond. That's the minimap. Camera vision, outside camera, camera vision, outside camera. Okay. Figure 1A. This representation of actions result in approximately 10 to the 26 possible choices as at each step. Similar to human players, a special action is available to move the camera view, so as to gather more information. Humans play Starcraft under physical constraints that limit their reaction time and the rate of their actions. The game was designed with these limitations in mind, and removing those constraints changes the nature of the game. We therefore choose to impose constraints upon Alpha Star. It suffers from delay due to network latency and computation time, and its actions per minute (APM) are limited with peak statistics substantially lower than that of humans. Figure 2C 3G for performance analysis. Alpha Star's figure 2C. Figures 2C. Distribution of effective actions per minute, EPM, as reported by Starcraft II for both Alpha Star Final Blue and human players Red. Okay, average. Blue is Alpha Star Final. So the EPM is slightly higher for the blue. Dash lines show mean values. Icons reproduce with permission from Blizzard. Okay, and (3G) APM limits. APM limits relative to those used in Alpha Star. Reducing APM substantially reduces performance. Unexpectedly, increasing APM also reduces performance, possibly because the agent spends more time on refining microtactics than on learning diverse strategies. Okay. Figures 2C and 3G for performance analysis. Alpha Stars play for performance analysis. Alpha Stars play with this interface in these constraints was approved by a professional player. See professional player statement in methods. Learning algorithm. To address the complexity and game theoretic challenges of StarCraft, Alpha Star uses a combination of new and existing general purpose techniques for neural network architectures, imitation learning and reinforcement learning, and multi-agent learning. Further details about these techniques are given in the methods. Central to Alpha Star is a policy pi theta AT given ST and Z, which is equal to the probability of AT given ST and Z, represented by a neural network with parameters theta, theta for the policy pi theta, that receives all observations ST, which is equal to O, 1 to T, all the observations, and A, 1 to T minus 1. So ST has all the observations and all the actions from the start of the game as inputs, and select actions as outputs. The policy is also conditioned on a statistic Z that summarizes a strategy sampled from human data. For example, a build order. Our agent architecture consists of general-purpose neural network components that handle StarCraft's raw complexity. Observations of player and opponent units are processed using a self-attention mechanism. To integrate spatial and non-spatial information, we introduce spatial connections. To deal with partial observability, the temporal sequences of observations is processed by a deep long short-term memory (LSTM) system. To manage the structured combinatorial action space, the agent uses a auto-regressive policy. And recurrent pointer network. Extended data. Figure 3 summarizes the architecture, and figure 3F shows the ablation of each component. So 3F, scatter components, transformer, pointer network. What does it say? 3F. Figure 3. Ablation for key components of Alpha Star. These experiments use a simplified setup. One map, Kairos junction, one race matchup, Protoss versus Protoss, reinforcement learning and leak experiments limited to 10 to the 10 steps. Only main agents and 50 to 50% mix of cell play and PFSP unless stated otherwise. The first column shows ELO ratings. First column. This way, first column. Against ablation test agents, each rating was estimated with 11,000 full games of Starcraft II. AB. Comparing different league compositions using ELO of the margin agents A and relative population performance of the whole leagues B. League composition. Okay, but we're only interested in architecture. Scatter connections, transformer, supervised win rate with elite bot. So scatter connections seems to be the highest, which it's introduced in this paper. Transformer, 71%, pointer network, action delays, and 0% with baseline. That's without any of these. Okay. So extended data figure 3 summarizes the architecture, and figure 3F shows the ablation of each component. Agent parameters were initially trained by supervised learning. Games were sampled from a publicly available dataset of anonymized human replays. The policy was then trained to predict each action AT, conditioned either solely on ST or also on Z. The result in a diverse set of strategies. This results in a diverse set of strategies that reflect the modes of human play. The agent parameters were subsequently trained by a reinforcement learning algorithm that is designed to maximize the win rate. That is, compute a best response against a mixture of opponents. The choice of opponent is determined by multi-agent procedure described below. AlphaStar's reinforcement learning algorithm is based on a policy gradient algorithm similar to Advantage Actor Critic. 13 is asynchronous methods for deep reinforcement learning. Proceedings. Okay, that's the reference. Updates were applied asynchronously. Impala distributed deep RL with importance weighted actor learner architecture. Okay, Impala and replayed experience. So sample efficient actor critic experience replay. This requires an approach known as off-policy learning. Off-policy learning, Barton and Soto. Okay. That is updating the current policy from experience generated by a previous policy. Our solution is motivated by the observation that in large action spaces, the current and previous policies are highly unlikely to match over many steps. We therefore use a combination of techniques that can learn effectively despite this mismatch. Temporal difference learning, TD lambda, 16, learning Sutton are learning to predict by method of temporal differences. Okay, TD lambda. Clipped importance sampling, vtrace. Vtrace is back to Impala again. And the new self-imitation algorithm, UPGO, that moves the policy towards trajectories with better than average rewards. Self-imitation learning. Okay. So the problem is this requires an approach known as off-policy, which is our solution is motivated by the observation that in large action spaces, the current and previous policies are highly unlikely to match over many steps. Okay. Policy changes over time. Okay. To reduce variance during training only, the value function is estimated using information from both the players and the opponent's perspectives. Figure 3i to k analyzes the relative importance of these components. Okay, figure 3i and k of policy learning. So UPGO TD lambda, adding TD lambda, and starting with vtrace, and that was 3i and 3k. Value function with opponent info and not without opponent info. Okay, so the opponent, adding the opponent info adds a lot to the value function. One of the main challenges in StarCraft is to discover novel strategies. Consider a policy that has learned to build and utilize the micro-tactics of ground units. Any deviation that builds and naively uses air units will reduce performance. It is highly improbable that the naive exploration will execute a precise sequence of instructions over thousands of steps that constructs air units and effectively utilizes their micro-tactics. To address this issue and to encourage robust behavior against likely human play, we utilize human data. Each agent is initialized to the parameters of the supervised learning agent. Subsequently, during reinforcement learning, we either condition the agent on a statistic z, in which case agents receive a reward for following the strategy corresponding to z, or train the agent unconditionally, in which case the agent is free to choose its own strategy. Agents also receive a penalty whenever their action probabilities differ from the supervised policy. The human exploration ensures that a wide variety of relevant modes of play continue to be explored throughout training. Figure 3e shows the importance of human data in Alpha Star. Okay, so there's a huge amount of imitation learning, and which is in this statistic z. Okay, so figure 3e, and no human data, supervised human data, supervised learning, human initialization, supervised KL, and statistic Z, so that adds a lot. To address the game theoretic challenges, we introduce league training, an algorithm for multi-agent reinforcement learning, so 1B and C. Okay, so league training. So could be Alpha Star is trained via both supervised learning and reinforcement learning. In supervised learning bottom, this is the supervised learning part, so human OT is the observation, Z is statistics and action, and pi T SL, and T is probably time. Okay. Alpha Star is trained via both supervised and reinforcement learning. In supervised learning bottom, the parameters are updated to optimize the callback libeler KL divergence between its output and human actions sampled from a collection of replays. In reinforcement learning top, the human data in reinforcement learning top, human data are used to sample the statistic Z, and agent experience is collected to update the policy and value outputs via reinforcement learning. TD lambda, vtrace, UPGO combined with a KL loss towards the supervised agent. So human data are used to sample the outside statistic, and the agent experience is collected to update the policy and value outputs via reinforcement learning. So here it just learns the actions without an opponent. Here there's a reinforcement learning, and there's an opponent, and there's a reward. So the agent observes something. Where's the action? It's a policy and it's being updated. I think this is the value function for the actor critic. This is the policy. The value is being updated. The policy is being updated. And the rewards feedback here. Okay. No. Okay, let's go to C. 3 pools of agents, each initialized by supervised learning, were subsequently trained with reinforcement learning. As they train, these agents intermittently add copies of themselves, players that are frozen at specific point, to the league. The main agents train against all of these past players as well as themselves. The league exploiters train against all past players. The main exploiters train against the main agents. Main exploiters and league exploiters can be reset to the supervised agent when they add a player to the league. Okay, human data, past players, current players, main exploiters, league exploiters, supervised players. Red is matchmaking target, orange is reinforcement learning, supervised learning, and reinitialization. Okay. To address the game theoretic challenges, we introduced league training, an algorithm for multi-agent reinforcement learning. Self-play algorithms similar to those used in chess and Go learn rapidly but may chase cycles. For example, where A defeats B and B defeats C, but A loses to C, indefinitely without making progress. 19. Open-ended learning in symmetric zero-sum games. Chess and Go. Okay, Chess and Go reference is general reinforcement learning algorithm that masters chess, shogi, and go through self-play. Fictitious self-play, FSP, avoids cycles by computing a best response against a uniform mixture of all previous policies. The mixture converges to a Nash equilibrium in two-player zero-sum games. So it's 20 to 22. Iterative solutions of game by fictitious play, generalized weak and fictitious play, and fictitious self-play in extensive form games. We extend this approach to compute a best response against a non-uniform mixture of opponents. This league of potential opponents include a diverse range of agents, as well as their policies from current and previous iterations. Figure 4D. Figure 4. Alpha star training progression. So training ELO, training days. Main agents, lead exploiters, main exploiters. Training ELO scores of agents in the league during the 44 days of training. Each point represents a past player evaluated against the entire league and the elite built-in box, where ELO is set to 0. B. Proportion of validation agents that beat the main league in more than 80 out of 160 games. This value increased steadily over time, which shows the robustness of league training to unseen strategies. C. The Nash distribution mixture of the least exploitable players. Of the players in the league as training progressed. It puts the most weight on recent players, suggesting that latest strategies largely dominate earlier ones, without much forgetting or cycling. For example, player 40 was part of the Nash distribution from its creation at day 20 until 5 days later, where it was completely dominated by newer agents. So now player 40 okay. Part D. And number of agents in the league. Average number of each units built by the Protoss agent over the course of league training. Normalized by the most common unit. Unlike the main agents, the exploiters rapidly explore different unit compositions. Worker units have been removed for clarity. Okay, this league of potential opponents include a diverse range of agents, as well as their policies from both current and previous iterations. At each iteration, each agent plays games against opponents sampled from mixtures specific to that agent. The parameters of the agent are updated from the outcomes of those games by the actor-critic reinforcement learning procedure described above. So the parameters of the agent are updated by actor-critic. The league consists of three distinct types of agents, differing primarily in the mechanism for selecting the opponent mixture. First, the main agent utilizes a prioritized fictitious self-play (PFSF) mechanism that adapts the mixture probability proportionally to the win rate of each opponent against the agent. This provides an agent with more opportunities to overcome the most problematic opponents. With fixed probability, a main agent is selected as an opponent. This recovers the rapid learning of self-play. Your 3C. Multi-agent learning. Second, main exploiter agents play only against the current iteration of main agents. Their purpose is to identify potential exploits in the main targets. The main agents are thereby encouraged to address their weaknesses. Third, League exploiter agents use a similar PFSF mechanism to the main agents, but are not targeted by main exploiter agents. Their purpose is to find systemic weakness of the entire league. Both main exploiters and league exploiters are periodically reinitialized to encourage more diversity and may rapidly discover specialist strategies that are not necessarily robust against exploitation. Figure 3b analyzes the choice of agents within the league. Figure 3b, league exploiters, and main agents. Figure 3b analyzes the choice of agents within the league. In Starcraft, each player chooses one of the three races, Terran, Protoss, or Zerg, each with distinct mechanics. We train the league using three main agents, one for each Starcraft race, three main exploiter agents, one for each race, and 6 league exploiter agents, 2 for each race. Each agent was trained using 32 third-generation tensor processing units, TPUs, over 44 days. During league training, almost 900 distinct players were created. Empirical evaluation. We evaluated the 3 main Terran, Protoss, Zerg, Alpha Star agents using the unconditional policy on the official online matchmaking system Battle.net. Each agent was assessed at 3 different snapshots during training. After supervised training only, Alpha Star supervised. After 27 days of league training, Alpha Star mid. And after 44 days of league training, Alpha Star final. Alpha Star supervised and Alpha Star mid were evaluated starting with an unranked rating on Battle.net for 30 to 60 games respectively. For each race, Alpha Star Final was evaluated from Alpha Star Mid's rating for an additional of 30 games for each race. The Battle.net matchmaking procedure selected maps and opponents. matches were played under blind conditions. Alpha Star was not provided with the opponent's identity and played under an anonymous account. These conditions were selected to estimate Alpha Star's strength under approximately stationary conditions, but do not directly measure its susceptibility to exploitation under repeated play. Alpha Star Final achieved a rating of 6275, matchmaking rating MMR for Protoss, 6048 MMR for Terran, and 5835 MMR for Zerg, placing it above 99.8% of ranked human players, and at Grandmaster level for all three races. Okay, Figure 2A. Figure 2A. So this is the Master, Grandmaster, Alpha Star Final, Alpha Star Mid. On Battle Figure 2 results. On Battle.net, Starcraft II players are divided into 7 leagues from Bronze to Grandmaster. Bronze to Grandmaster according to their ratings MMR. We played 3 variants of Alpha Star on Battle.net. Alpha Star Supervised, Alpha Star Mid, and Alpha Star Final. The Supervised agent was rated in the top 16% of human players, the midpoint agent within top 0.5%, and the final agent on average within the top 0.15%, achieving a Grandmaster level rating for all 3 races. So Alpha Star Supervised, Alpha Star Mid, and Alpha Star Final. B. MMR ratings of Alpha Star Final race from top to bottom. Alpha Star ratings versus opponents encountered on Battle.net from left to right, all races combined, Protoss, Terran, and Zerg. So Alpha Star race, probably the rating against the other race. Note that per race data are limited. Alpha Star won all Protoss versus Terran games. C. This one. Distribution of effective actions per minute, EPM as reported by Starcraft II for both Alpha Star Final, blue, and human players, red. Dashed lines show mean values, icons reproduced with permission. Okay. For Zerg. Figure 2A, extended data. Figure 7, analysis, supplementary data, replays, game replays. Alpha Star Supervised reading, Alpha Star Supervised reached an average rating of 3699, which places it above 84% of human players and shows the effectiveness of supervised learning. To further analyze Alpha Star, we also ran several internal ablations, Figure 3, and evaluations, Figure 4. For multi-agent dynamics, we ran a round-robin tournament of all players throughout the league training, and a second tournament of main agents held out validation agents trained to follow specific human strategies. The main agent performance improved steadily over all 3 races. The performance of the main exploiters actually reduced over time, and main agents performed better against the held-out validation agents, both of which suggest that the main agent grew increasingly robust. The league national equilibrium over all players at each point in time assigns small probabilities to players from previous iterations, suggesting that the learning algorithm does not cycle or regress. Finally, the unit composition changed throughout the league training, which indicates a diverse strategic progression. So all players at each point in time assign small probabilities to players from the previous iteration. Okay, so there's no forgetting. Conclusion. Alpha Star is the first agent to achieve Grandmaster level in Starcraft II and the first to reach the highest league of human players in a widespread professional esport without simplification of the game. Like StarCraft, real-world domains such as personal assistants, self-driving cars, or robotics require real-time decisions over combinatorial or structured action spaces given imperfectly observed information. Furthermore, similar to StarCraft, many applications have complex strategy spaces that contain cycles or hard exploration landscapes, and agents may encounter unexpected strategies or complex edge cases when deployed in the real world. The success of Alpha Star in Starcraft II suggests that general-purpose complex learning algorithms may have a substantial effect on complex real-world problems. Online content. Any methods, additional references, nature research, reporting summaries, source data, extended data, supplementary information, acknowledgements, peer review information, details of authors, etc. is in this website. Okay, and these are references. Okay, let's go to methods. Methods, game and interface. Game environment. StarCraft is a real-time strategy game that takes place in a science fiction universe. The franchise from Blizzard Entertainment comprises StarCraft, Brood War, and StarCraft II. In this paper, we use StarCraft II. Since StarCraft was released in 1998, there has been a strong competitive community with tens of millions of dollars of prize money. The most common competitive setting of StarCraft II is 1 versus 1, where each player chooses one of the 3 available races, Terran, Protoss, and Zerg, which all have distinct units and buildings, exhibit different mechanics, and necessitate different strategies when playing for and against. There's also a random race where the game selects the player's race at random. Players begin with a small base and a few worker units, which gather resources to build additional units and buildings, scout the opponent, and research new technologies. A player is defeated if they lose all buildings. There is no universally accepted notion of fairness in real-time human-computer matches, so our match conditions, interface, camera view, and action rate limits and delays were developed in consultation with professional StarCraft II players and Blizzard employees. Alpha Star's play under these conditions was professional player approved. See the professional player statement below. At each agent step, the policy receives an observation OT and issues an action AT, extended data tables 1 and 2, through the game interface. There can be several game time steps, each 45 milliseconds per agent step. Camera view. Humans play StarCraft through a screen that displays only part of the map, along with a high-level view of the entire map, to avoid information overload, for example. The agent interacts with the game through a similar camera-like interface, which naturally imposes an economy of attention, so that the agent chooses which area it fully sees and interacts with. The agent can move the camera as an action. Opponent units outside the camera have certain information hidden, and the agents can only target within the camera for certain actions, for example, building structures. Alpha Star can target locations more accurately than humans outside the camera, although less accurately within it, because target locations selected on a 256 by 256 grid are treated the same inside and outside the camera. Agents can also select sets of units anywhere, which humans can do less flexibly using control groups. In practice, the agent does not seem to exploit these extra capabilities. See the professional player statement below because of the human prior. Ablation data in figure 3H shows that using this camera view reduces performance. 3H, interface, non-camera interface and camera interface. Okay, using camera reduces performance. This is the win rate versus elite bot. Okay. APM limits. Humans are physically limited in the number of actions per minute, APM, they can execute. Our agents has a monitoring layer that enforces APM limitations. This introduces an action economy that requires action to be prioritized. Agents are limited to executing at most 22 non-duplicate actions per 5-second window. Converting between actions and the APM measured by the game is non-trivial, and agent actions are hard to compare with human actions. Computer can precisely execute different actions from step to step. Figure 2C and the extended Figure 1 for APM details. Figure 2C. EPM. Okay, distribution of effective actions per minute as reported. And both of them have similar EPMs. Delays. Humans are limited in how quickly they react to new information. AlphaStar has two sources of delay. First, in real-time evaluation, non-training. AlphaStar has a delay about 110 milliseconds between when a frame is observed and when an action is executed, owing to latency, observation, processing, and inference. Second, because agents decide ahead of time when to observe next, on average 300 milliseconds but possibly multiple seconds, they may react late to unexpected situations. The distribution of these delays is shown in extended data figure 2. Related work. Games have been the focus of artificial intelligence research for decades as a stepping stone towards more general applications. Classic board games such as chess and Go have been mastered using general-purpose reinforcement learning and planning algorithms. 18. A general reinforcement learning algorithm that paper. Reinforcement learning methods have achieved substantial success in video games such as those on the Atari platform, Super Mario Bros., Quake 3 Arena, Capture the Flag, and Dota 2. Real-time strategy RTS games are recognized for their game theoretic and domain complexities. Many subproblems of RTS games, for example, micromanagement, base economy, or build order optimizations, have been studied in depth, often in small-scale environments. For the combined challenge, the Starcraft domain has emerged by consensus as a research focus. Starcraft Brood War has an active competitive AI research community, and most bots combine rule-based heuristics with other AI techniques such as search, data-driven build order selection, and simulation. Reinforcement learning has also been studied to control units in the game. 734. 734. 734. Okay. 7 is Starcraft II, a new challenge for reinforcement learning. 34. Episodic explorations for deep deterministic policies and application to Starcraft micromanagement tasks. And 42 to 46. Overmind, learning micromanagement in Starcraft from replays using deep reinforcement learning. Deep learning. Forward modeling for partial observation strategy games. A Starcraft defogger. And imitation learning has been proposed to learn unit and building compositions. Learning micromanagement. Most recently, deep learning has been used to predict future game states. Starcraft II similarly has an active bot community. 46. Forward modeling for partial observation strategy games. A Starcraft defogger. Okay, that one. 7. Bot. Starcraft II, a new challenge. For reinforcement learning. No Starcraft bots have defeated professional players or even high-level casual players. And the most successful bots have used superhuman capabilities such as executing tens of thousands of APM or viewing the entire map at once. These capabilities make the comparison against humans hard and invalidate certain strategies. Some of the most recent approaches use reinforcement learning to play the full game, with handcrafted high-level actions or rule-based systems with machine learning incrementally replacing components. By contrast, AlphaStar uses a model-free end-to-end learning approach to play Starcraft II that sidesteps the difficulties of search-based methods that result from imperfect models, and is applicable to many domains that share some of the challenges present in StarCraft. Dota 2 is a modern competitive team game that shares some complexities of RTS games such as StarCraft, including imperfect information and large time horizons. Recently, OpenAI 5 defeated a team of professional Dota 2 players and a 99.4% of online players. Okay, 30. 30. OpenAI 5. The hero units of OpenAI 5 are controlled by a team of agents trained together with a scaled-up version of PPO. PPO is the Proximal Policy Optimization, based on handcrafted rewards. However, unlike AlphaStar, some game rules were simplified. Players were restricted to a subset of heroes. Agents used hard-coded subsystems for certain aspects of the game, and agents did not limit their perception to a camera view. AlphaStar relies on imitation learning combined with reinforcement learning, which has been used several times in the past. Similarly to the training pipelines of AlphaStar, the original AlphaGo initialized a policy network by supervised learning from human games, which was then used as a prior in Monte Carlo tree search. Similar to a statistic Z, other work attempted to train reward functions from human preferences and use them to guide reinforcement learning, or learn goals from human intervention. Reward learning from human preferences and demonstrations in Atari. Overcoming exploration in reinforcement learning with demonstrations. 52. Deep reinforcement learning from human preferences. Related to the League, recent progress in multi-agent research has led to agents performing at human level in Capture the Flag team mode in Quake 3 Arena. 29. Human level performance in 3D multiplayer games with population-based reinforcement learning. These results were obtained using population-based training of several agents competing with each other, which use pseudo-reward evolution to deal with hard credit assignment problem. Similarly, the policy space response oracle framework, a unified game theoretic approach to multi-agent reinforcement learning. Similarly, the policy space response oracle framework is related to League training. Although League training specifies unique targets for approximate best responses, that is, PFSB and exploiters. Architecture. The policy of AlphaStar is a function pi theta at given stz, which maps all previous observation actions st equals 0, 1 to t, a, 1 to t minus 1. So state has all the observations and all the previous actions defined in extended data tables 1 and 2. So extended data table 1, agent input space, category, field description, unit type, drone or force field, owner, agent, opponent or neutral, status, current health, shields, energy, display type, examples, snapshots or opponent buildings in the fog of war, position, entity position, number of workers for resource collecting, base buildings, cooldowns, and attack cooldown attributes, invisible powered hallucination active in cargo and in the ocean, unit attributes, example, biological or armored, cargo status, current and maximum amount of cargo space, building status, build progress, build queue and add-on type, resource status, remaining resource content, order status, order queue and order progress, buff status, buffs and buff durations. And these are the entities. Map 128 by 128 grid, height of the map locations, visibility, whether the map locations are currently visible, creep, whether there's a creep at a specific location, entity owners, which player owns entities, alerts, whether units are under attack, pathable, which areas can be navigated over, buildable, which areas can be built on. Player data, race, agent and opponent requested race, and agent actual race. Upgrades, agent upgrades and opponent upgrades, if they would be known to humans. Agent statistics, agent current resources, supply, army army supply, worker supply, maximum supply, number of idle workers, number of warp gates, and number of larvae. Game statistics. Current camera position. The camera is 32 by 20 game unit size rectangles. Current time in game. The observations received by the agent through raw interface. Information is hidden if it would be hidden from a human player. For example, Alpha Star will not see most information about invisible opponents unless there's a detector. Opponents' units hidden by fog of war will not appear in the list of units. Opponent units outside the agent's camera view will have only the owner, display type, and position. An opponent's cloaked units will appear in the list only if they are within the agent's camera view. Note that this interface displays information that must be inferred or remembered by humans, such as the armor upgrades of a visible opponent unit, attack cooldowns, or entities that are occluded by other entities. Okay, extended data table 2, agent action space. Action type. Which action to execute? Some examples of actions are moving a unit, training a unit in a building, moving the camera, or no op. See PySC2 for full list. 7. Selected units, entities that will execute the action. Target, an entity or location in the map discretized to 250 by 256 targeted by the action. Queued, whether to queue the action or execute it immediately. Repeat, whether or not to issue the action multiple times. Delay, the number of game time steps to wait until receiving the next observation. The action arguments that the agents can submit to the raw interfaces as part of the action. Some fields may be ignored depending on the action type. Okay, these are the actions that can be taken and the observations that are from the table. And Z, representing strategy statistics to a probability distribution over actions AT for the current step. PyTheta is implemented as a deep neural network with the following structure. The observations OT are encoded into vector representations, combined and processed by a deep LSTM, which maintains memory between steps. The action arguments AT are sampled autoregressively. Recurrent neural network-based language model. Auto-regressively conditioned on the outputs of the LSTM and conditions on the outputs of the LSTM and the observation encoders. There is a value function for each of the possible rewards. See reinforcement learning. Architecture components were chosen and tuned with respect to their performance in supervised learning, and include many recent advances in deep learning architectures. Okay, 7, 8, so the transformer, 12, pointer networks, 54, film visual reasoning with a general conditioning layer, and 55. Deep residual learning for image recognition. A high-level overview of the agent architecture is given in Extended Data Figure 3. Extended Data Figure 3. Okay, Extended Data Figure 3. Overview of the architecture of Alpha Star. A detailed description is provided in the supplementary data, detailed architecture. Okay, so baseline features, value network, action type residual MLP, delay MLP, pointer network, attention, scalar features, transformer, entities, minimap, spatial encoder, ResNet, input, neural network, output, action. Okay, this is the input. This is the neural network. Blue is the neural network. B is the red is the output. That's the action. Okay, so there's MLP, transformer, ResNet. MLP for scalar features, entities for transformer. Minimap is ResNet. Goes to deep LSTM. MLP. Residual MLP, pointer network, attention, decon, ResNet. With more detailed descriptions and supplementary data, detailed architecture. AlphaStar has 139 million weights, but only 55 million weights are required during inference. Ablation figure 3F compares the impact of SCADA connections, transformer, and pointer networks. So 3F, yep, this one. SCADA connections, adding transformer, adding pointer network, extra delays, and baseline. Supervised learning. Each agent is initially trained through supervised learning on replays to imitate human actions. Supervised learning is used both to initialize the agent and to maintain diverse exploration. 56. Distinct knowledge in a neural network. Because of this, the primary goal is to produce a diverse policy that captures StarCraft's complexities. We use a data set of 971,000 replays played on StarCraft II versions 4.8.2 to 4.8.6 by players with NMR scores, Blizzard's metrics similar to ELO greater than 3,500. That is from the top 22% of players. Instructions for downloading replays can be found at github.com/blizzard s2 client proto. The observations and actions are returned by the game's raw interface. Extended data tables 1 and 2. We train one policy for each race with the same architecture as the one during reinforcement learning. From each replay, we extract a statistic Z that encodes each player's build order, defined as the first 20 constructed buildings and units, and cumulative statistics, defined as the units, buildings, effects, and upgrades that were present during a game. We condition the policy on Z in both supervised and reinforcement learning. And in supervised learning, we set Z to 0 10% of the time. To train the policy at each step, we input the current observations and output probability distributions over each action argument. Extended data table 2, so the action defines all the actions. For these arguments, we compute the KL divergence between human actions and the policy's outputs and apply updates using the Atom optimizer. We also apply L2 regularization. The pseudocode of the training algorithm can be found in this supplementary data. We further fine-tune the policy using winning replays with MMR above 6,200, 16,000 games. Fine-tuning improved the win rate against built-in Elite Bot 87% to 96% in Protoss versus Protoss games. The fine-tuned supervised agents were rated at 3947 MMR for Terran, 3607 MMR for Protoss, and 3544 MMR for Zerg. They are capable of building all units in the game and are qualitatively diverse from game to game. Extended data figure 4. Figure 4. AlphaStar supervised and AlphaStar final. Distribution of units built in game. Units built by Protoss AlphaStar supervised left and AlphaStar final right over multiple self-play games. AlphaStar supervised can build every unit. So game number and game number. So the number of different things that were built. Reinforcement learning. We apply reinforcement learning to improve the performance of AlphaStar based on agent versus agent games. We use the match outcome, -1 on loss, 0 on draw, and +1 for win, as the terminal reward RT without a discount to accurately reflect the true goal of winning games. Following the actor-critic paradigm. 14 Impala. A value network V theta ST of Z is trained to predict RT and used to update the policy pi theta AT ST given ST and Z. Starcraft poses several challenges when viewed as a reinforcement learning problem. Exploration is difficult, owing to domain complexity and reward sparsity. Policies need to be capable of executing diverse strategies throughout training, and off-policy learning is difficult, owing to the large time horizons and complex action space. Exploration and diversity. We use human data to aid in exploration and to preserve strategic diversity throughout training. First, we initialize the policy parameters to the supervised policy and continually maximize the KL divergence between the supervised and current policy. So 59, policy distillation. 60, actor mimic, deep multitask and transfer reinforcement learning. Second, we train the main agents with pseudo rewards to follow a strategy, statistic Z, which we randomly sample from human data. These pseudo rewards measure and edit distance between sampled and executed build orders, and the Hamming distance between sampled and executed cumulative statistics. Each type of pseudo reward is active, that is non-zero with probability 25%, and separate value functions and losses are computed for each pseudo reward. We found our use of human data to be critical in achieving good performance with reinforcement learning. Value and policy updates. New trajectories are generated by actors. Asynchronously, model parameters are updated by learners using a replay buffer that stores trajectories. Because of this, AlphaStar is subject to off-policy data, which potentially requires off-policy corrections. We found that existing off-policy correction methods can be inefficient in large structured action spaces, such as that used for Starcraft, because distinct actions can result in similar or even identical behavior. We address this by using a hybrid approach that combines off-policy correctness for the policy, which avoids instability, and an uncorrected update of the value function, which introduces bias but reduces variance. Specifically, the policy is updated using vtrace, and the value estimates are updated using TD lambda ablation in Figure 3I. When applying vtrace to the policy in large action spaces, the off-policy corrections truncate this trace early. To mitigate this problem, we assume independence between the action type, delay, and all other arguments. So update the components of the policy separately. To decrease the variance of the value estimates, we also use the opponent's observations as input to the value functions. Note that these are used only during training, as value functions are unnecessary during evaluation. In addition to the vtrace policy update, we introduce an upgoing policy update, UPGO, which updates the policy parameters in the direction of rho T, the off-policy ratio, GT, probably return, time, U, V theta, the value function over the state and the statistic, the gradient with respect to theta of the log of the policy, where GT is RT plus GT plus 1U if the Q value of ST plus 1 is greater than the value of ST1, or it's equal to the value. So the return is updated if the Q value is better than the value, whichever is bigger is being updated as the return, where is an upgoing return. QSTAZ is an action value estimate. Rho T equals min of pi theta AT given ST and Z, and over pi theta prime, AT given ST and Z, or 1 is the min of those, is a clipped importance ratio, and pi theta prime is a policy that generates the trajectory in the actor. Similar to self-imitation learning, 17, self-imitation learning, the idea is to update the policy from partial trajectories with better than expected returns by bootstrapping when the behavior policy takes a worse than average action. Owing to the difficulty of approximating QSTATZ over the large action space of Starcraft, we estimate action values with a one-step target. QSTATZ is equal to this. So it's the reward plus the value. The overall loss is a weighted sum of the policy and value function losses described above, corresponding to the win-loss reward RT as well as pseudo-reward based on human data, the KL divergence loss with respect to the supervised policy, and the standard entropy regularization loss. 13. Synchronous methods for deep reinforcement learning. We optimize the overall loss using ATOM. The pseudocode of reinforcement learning algorithm can be found in supplementary data. Multi-agent learning. League training in multi-agent reinforcement learning that is designed both to address cycles commonly encountered during self-play training and to integrate a diverse range of strategies. During training, we populate the league by regularly saving the parameters from my agents that are being trained by the RL algorithm as new players, which have fixed frozen parameters. We also continuously reevaluate the internal payoff estimation, giving agents up-to-date information about their performance against all players in the league. See evaluators in the extended dataset figure 6. Extended figure 6, evaluators. Coordinator, the agent, the environment's actors, evaluators. Prioritize fictitious self-play. Our self-play algorithm plays games between the latest agents for all three races. This approach may chase cycles in strategy space and does not work well in isolation. Figure 3D. Prioritize FSF is the fictitious self-play. Prioritized. It does not work well if you don't have prioritized self-play. Self-play will has lower win ratio. Okay, FSB fictitious self-play 20 to 22. Iterative solutions to games by fictitious play, generalized weakened fictitious play, fictitious self-play, and extensive form games. Avoid cycles by playing against all previous players in the league. However, many games are wasted against players that are defeated in almost 100% of games. Consequently, we introduced PFSP. Instead of uniformly sampling opponents in the league, we use the matchmaking mechanisms to promote a good learning signal. Given a learning agent A, we sample the frozen opponent B from candidate C with probability F, probability that A beats B over P, A beats C over all C in the space. Where F goes from 0, 1 to 0 to infinity is some weighing, takes a probability in some weighing function. Choosing F hard X equals 1 minus X to the P makes PFSP focus on the hardest players, where P is a real number, controls how entropic the resulting distribution is. As F hard 1 equals 0, no games are played against opponents that the agent already beats. By focusing on the hardest players, the agent must beat everyone in the league rather than maximizing average performance, which is even more important in highly non-transitive games such as Starcraft. Extended data figure 8. Figure 7, figure 8. Payoff matrix, limited to only Protoss versus Protoss games for simplicity, split into agent types of the league. Blue means a row agent wins, red loses, and white draws. The main agent behaves transitively. The more recent agents win consistently against older main agents and exploiters. Interaction between exploiters are highly non-transitive across the full payoff. There are around 3 million rock, paper, scissors cycles with requirements of at least 7% wins to form a cycle that involves at least one exploiter, and around 200 that involve only main agents. Main agents versus main agents. First is league exploiter 1, league exploiter 2, and main exploiter. And Okay, extended data figure. By focusing on the hardest players, the agent must beat everyone in the league rather than maximizing average performance, which is even more important in highly non-strategy games such as Starcraft, where the pursuit of the mean win rate might lead to policies that are easy to exploit. This scheme is used as the default weighing of PFSP. Consequently, on the theoretical side, one can view F-hard as a form of smooth approximation of max-min optimization, as opposed to max average, which is imposed by FSP. In particular, this helps with integrating information from exploits, as these are strong but rare counter strategies, and a uniform mixture would be able to just ignore them. Extended data figure 5. A more detailed analysis of multi-agent ablations from figure 3 and D. Prioritize fictional self-play PSFP training outperforms FSP under all measures considered. It has stronger population measured by relative population performance, provides a less exploitative solution and has better final agent performance against the corresponding league. So this is PFSP, test agents. Okay. Only playing against the hardest opponents can waste games against much stronger opponents. So PFSP also uses an alternative curriculum, F var x equals x1 minus x, where the agent preferentially plays against opponents around its own level. We use this curriculum for many exploiters and struggling main agents. Populating the league. During training, we use 3 agent types that differ only in the distribution of opponents they train against, while they are re-snapshotted to create a new player and the probability of resetting to the supervised parameters. Main agents are trained with a proportion of 35% SP, 50% PFSP against all players in the league, and an additional 50% of PFSP matches against forgotten main players the agent can no longer beat in past main exploiters. If there are no forgotten players or strong exploiters, the 15% is used for self-play instead. Every 2 times 10 to the 9 steps, a copy of the agent is added as a new player in the league. Main agents never reset. League exploiters are trained using PFSP, and their frozen copies are added to the league, where they defeat all players in the league in more than 70% of the games, or after a timeout of 2 times 10 to the 9 steps. At this point, there is a 25% probability that the agent is reset to the supervised parameters. The intuition is that the league exploiters identify global blind spots in the league, strategies that no player in the league can beat, but that are not necessarily robust themselves. Main exploiters play against human agents. Main exploiters play against main agents half of the time, and if the current probability of winning is lower than 20%, exploiters use PFSP with F-var weighting over players created by the main agents. This forms a curriculum that facilitates learning. Otherwise, there is enough learning signal, and it plays against the current main agents. These agents are added to the league whenever all 3 main agents are defeated in more than 70% of the games, or after a timeout of 4 times 10 to the 9 steps. They are then reset to the supervised parameters. Main exploiters identify weaknesses of main agents and consequently make them more robust. For more details, refer to the supplementary data. Infrastructure. In order to train the league, we run a large number of Starcraft II matches in parallel and update the parameters of the agents on the basis of data from those games. To manage this, we developed a highly scalable training setup with different types of distributed workers. For every training agent in the league, we run 16,000 concurrent Starcraft II matches and 16 actor tasks, each using a TPU version 3 device with all 8 TPU cores to perform inference. In data center performance analysis of tensor processing unit. Okay. To perform inference. The game instances progress asynchronously on preemptible CPUs, roughly equivalent to 150 processors with 28 physical cores each. But requests for agent steps are batched together dynamically to make efficient use of the TPU. Using TPUs for batch inference provides large efficiency gains over previous work. 14 Impala, 29 human level performance in 3D multiplayer games with population-based reinforcement learning. Okay. Actors send sequences of observations, actions, and rewards over the network to a central 128-core TPU learner worker, which updates the parameters of the training agent. The received data are buffered in memory and replayed twice. The learner worker performs large batch synchronous updates. Each TPU core processes a mini batch of 4 sequences for a total batch size of 512. The learner processes about 50,000 agent steps per second. The actors update their copy of the parameters from the learners every 10 seconds. We instantiate 12 separate copies of the actor-learner setup, 1 main agent, 1 main exploiter, and 2 league exploiter agents for each StarCraft race. 1 central coordinator maintains an estimate of the payoff matrix, samples new matches on request, and resets main and league exploiters. Additional evaluator workers running on the CPU are used to supplement the payoff estimates. See extended data figure 6 for overview of the training setup. Figure 6 for the training setup. Okay. 128 TPU cores, agent, 16 tasks, CPU devices, environments, observations, coordinator, tasks. Evaluation. AlphaBattle.net evaluation. AlphaStar agents were evaluated against humans on Battle.net, Blizzard's online matchmaking system based on MMR ratings, on StarCraft II balance patch 4.93. AlphaStar Final was rated at Grandmaster level, above 99.8% of human players were active enough in the past month to be placed into a league on the European server, about 90,000 players. AlphaStar played only opponents who opted to participate in the experiment. The majority of the players opted in. 62 DeepMind research on ladder. Used an anonymous account name and played on 4 maps: Cyber Forest, Kairos Junction, Kings Cove, and New Repugnancy. Blizzard updated the map pool a few weeks before testing. Instead of retraining AlphaStar, we simply played on the 4 common maps that were kept in the pool of 7 available maps. Humans must also select at least 4 maps and frequently play under anonymous account names. Each agent ran on a single high-end consumer GPU. We evaluated at 3 points during the training: supervised, midpoint, and final. For the supervised and midpoint evaluation, each agent began with a fresh unranked account. Their MMR was updated on Battle.net as for humans. The supervised and midpoint evaluations played 30 and 60 games respectively. The midpoint evaluation was halted while still increasing because the anonymity constraint was compromised after 50 games. For the Battle.net evaluation, we used several accounts to parallelize games and help to avoid identification. The MMR of our accounts were seeded randomly from a distribution of combined estimated and midpoint MMRs. Consequently, we no longer use the iterative MMR estimation provided in Battle.net and instead use the underlying probabilistic model provided by Blizzard. Given our rating R with uncertainty U, the opponent rating R with uncertainty U between 0.1 and 1, the probability of the outcome, OI, it's probably different from observation. OI in -1 to 1, either win or loss, is probability of OI equals 1 equals RURI equals 1 minus the probability of losing, given these parameters, which is the phi is the cumulative distribution of a standard Gaussian distribution where we use battle.net's minimum uncertainties. U equals ui equals 0.1. So phi of r minus ri, 402 plus u squared, square root of u squared plus ui squared, phi of r minus ri over 568. Under independent and identically distributed assumptions of match results and uniform priors over MMRs, we can compute our ratings as argmax over all r in n, probability the reward over results, equals argmax probability results ur and argmax product of probability oi given r and ri. We validated our MMR computation on the 200 most recent matches of Dario TLO once, a professional Starcraft II player, and obtained an MMR estimate of 6334. The average MMR reported by Battle.net was 6336. Starcraft demonstration evaluation. In December 2018, we played 2 5-game series against Starcraft II professional players Gregords, Mana, Kommunitz, and Dario TLO once. Although TLO did not play the same Starcraft II race that he plays professionally. These games took place in a different preliminary version of Alpha Star. In particular, the agent did not have a limited camera, was less restricted in how often he could act, and played for and against a single StarCraft race on a single map. Alpha Star won all 10 games in both 5-game series, though an early prototype lost a fellow game against Mana. Analysis. Agent sets. For validation agents, we validated league robustness against a set of 17 strategies trained using only main agents and no exploiters, and fixing Z to a hand-curated set of interesting strategies, for example, a cannon rush or early flying units. Ablation test agents included the validation agents and the first, that is weaker 20 main and 20 lead exploiter Protoss agents created by full league training. For fixed opponents, to evaluate our reinforcement learning algorithm, we computed the best response against a uniform mixed strategy composed of the first 10 league exploiter Protoss agents created by league training. Metrics used in figures. To compute the internal ELO ratings of the league, we added the built-in bots and used them to estimate ELO with the following model. Probability that R1 beats R2 is given by 1 over the 1 plus negative exponent of R1 minus R2 over 400, which is equal to phi R1 minus R2 divided by 400. Where R1 and R2 are ELO ratings of both players. As the ELO ratings has no intrinsic absolute scale, we ground it by setting the rating of the built-in elite bot to 0. RPP is the expected outcome of the metagame between two populations after they reach the Nash equilibrium, given a payoff matrix. Between all agents in League A and B of sizes N and M respectively, PAB is between 0 and 1 times N by N. So RPP PAB equals Nash PAB transpose PAB Nash PBA, where Nash X is in between 0 and 1 to the kth power is a vector of probabilities assigning to playing each agent in League X of size K in the Nash equilibrium. High RPP means that the League A consists of agents that can form a mixed strategy that can exploit agents from League B while not being too exploitable by a mixed strategy from League B. Alpha Star generality. To address the complexity and game theoretic challenges of StarCraft, AlphaZero uses a combination of new and existing general-purpose techniques for neural network architectures, imitation learning, reinforcement learning, and multi-agent learning. These techniques and their combinations are widely applicable. The neural network architecture components, including the new SCADA connections, are all generally applicable to any domain whose observations comprise a combination of images, lists, and sets, all which are present in StarCraft. AlphaStar's action space is defined as a set of functions with typed arguments. Any domain which defines a similar API can be tackled with the same decomposition of complex structured action spaces, with joint probabilities decomposed by the chain rule, akin to, for example, language modeling or theorem proving. Imitation learning for AlphaStar requires a large number of human demonstrators to be effective, and thus is applicable only to those domains that provide such a set of demonstrations. Using a latent variable z to induce exploration is not specific to StarCraft, but the particular choice of statistics required domain knowledge. In particular, we chose z to encode openings and units in StarCraft. Pseudo rewards were based on appropriate distance metrics for these statistics, such as edit distance or having distance. AlphaStar's underlying reinforcement learning can be applied to any reinforcement learning environment. The use of an opponent observations for a lower variance baseline and a new component such as hybrid off-policy learning, UPGO, and distillation towards an imitation policy are also widely applicable. Lastly, we propose a new multi-agent training regime with different kinds of exploiters whose purpose is to strengthen the main agents. Together with PFSP, these are all general-purpose techniques that can be applied to any multiplayer domain. Professional player statement. The following code describes our interface and limitations from Starcraft II professional players Dario TLO once, who is part of the team and author of this paper. The limitations that have been put in place for AlphaStar now mean that it feels very different from the initial show match in January. While AlphaStar has excellent and precise control, it doesn't feel superhuman, certainly not at a level that a human couldn't theoretically achieve. It is better in some aspects than humans, and then also worse in others. But of course, there are going to be unavoidable differences between AlphaStar and human players. I've had the pleasure of providing consultation to the AlphaStar team to help ensure that DeepMind system does not have any unfair advantage over human players. Overall, it feels very fair, like it is playing a real game of StarCraft and doesn't completely throw the balance off by having unrealistic capabilities. Now that it has limited camera view, when I multitask, it doesn't always catch everything at the same time, so that aspect also feels very fair and more human-like. Reporting summary. Further information on research design is available in the Nature Research reporting summary link to the paper. Data availability. All the games in the AlphaStar Pathete Online can be found in the file replays.zip in the supplementary data, and the raw files from the battle.net experience can be found in bnet.json in the supplementary data. Code availability. The StarCraft II environment was open sourced in 2017 by Blizzard and DeepMind. All the human All human replays used for imitation learning can be found in GitHub Blizzard S2 Client Proto. The pseudocode for supervised learning, reinforcement learning, and multi-agent components of AlphaStar can be found in the file pseudocode.zip in the supplementary data. All the neural architecture details and hyperparameters can be found in the file detailarchitecture.txt in the supplementary data. Okay, Figure 1. Extended data figure 1. APM limits. Top. Win probability of AlphaStar supervised against itself when applying various agent rate limits. Our limit does not affect supervised performance and acceptable when compared to humans. So percentage of AlphaStar APM limit, win probability at 100%. Increasing it doesn't increase the win probability. Bottom. Distributions of APMs of AlphaStar, Final Blue, and Human Red during games on Battle.net. Dash lines show the mean values. Red one is okay. Red one is probably AlphaStar. Okay. Extended data figure 2. Delays. Left, distribution of delays between when the game generates an observation and when the game executes the corresponding agent action. So about 100 milliseconds. Right. Distribution of how long agents request to wait without observing between observations. And overview of the neural network architecture. Distributions of units built in the game. Analysis of multi-agent ablations. Training infrastructure. Extended data figure 7. Battle.net performance details. Top. Visualization of all matches played by AlphaStar Final. Right. and matches against a 4500 MMR of Alpha Star mid left. So Alpha Star mid, all matches played against 4500 MMR. What is green and what is red and what is blue? Red is empirical, 6k plus MMR. Alpha Star is blue, green is don't know. Okay. Each Gaussian represents an opponent MMR with uncertainty. Alpha Star won against opponents shown in green and lost to those shown in red. So one green and lost two reds. So all these ones were red, some of these red ones. The Alpha Star final goes much to the right and has some wins and some losses. And this is probably for Protoss. Much further to the right, Terran and Zerg. Blue is our MMR estimate, black is the MMR reported by Starcraft II. The orange background is the Grandmaster League range. Bottom win probability versus gap in MMR. The shaded gray region shows MMR model predictions when players' uncertainty is varied. The red and blue lines are empirical win rates for players above 6000 MMR and Alpha Star final respectively. Both human and Alpha Star win rates closely to follow the MMR model. So empirical 6k plus MMR, Alpha Star, MMR model prediction. Okay, and extended playoff matrix for the self-play and input data, action space, and reporting summary. And that's the end of the paper.